This presentation is about schedulability analysis for multi-core systems, accounting for resource stress and resource sensitivity. This research has been undertaken by myself, Rob Davis, David Griffin and Ian Bate, all of whom work in the Real-Time Systems Research Group at the University of York. So let's take a look at cross-core contention in multi-cores. Common off-the-shelf multi-core hardware is designed to deliver high average case performance at low cost. It achieves this by sharing hardware resources such as cache, interconnector bus and main memory between cores. Unfortunately, this leads to cross-core contention when co-running tasks attempt to access shared hardware resources at the same time. This contention extends task execution times compared to the standalone case. This increase in task execution times is referred to as interference. The problem of cross-core contention and interference has led to timing verification of multi-cores becoming a hot topic of real-time systems research over the past 10 years. Timing verification for multi-cores in academia has been summarised by Maser in a survey that was published in 2019. This survey classified over 120 research papers on the topic. The majority of the research discussed in the survey relies on detailed timing information about shared hardware resources and their arbitration policies. Unfortunately, there are substantial difficulties because information is often not disclosed by hardware vendors or is incomplete or even incorrect. And overall, the behaviour can become so complex as to preclude a static analysis that provides meaningful bounds rather than gross overestimates. By contrast, in industry, it's common practice to use measurement-based timing analysis. This is viable for well-designed systems on single-core platforms, but its direct extension to multi-core systems cannot provide an adequate solution that correctly bounds cross-core interference. So let's take a look at cross-core contention in multi-cores. A simple, naive approach would be to run the tasks in parallel, measure their execution times, and hence determine the amount of interference. Unfortunately, the maximum interference depends on the precise timing at which contention takes place. In other words, the timing of accesses to shared hardware resources by the task under analysis, and also the co-running tasks on other cores. This timing depends on the inputs to the tasks, the paths taken, and the data accessed. It also depends on the scheduling policy, the task start times, and any preemptions. Unfortunately, in practice, it's impossible to find the combination of behaviours that gives the maximum interference. So, to solve this problem, we need to somehow break it down. And the way we do that is to use the concepts of resource stress and resource sensitivity, in particular via resource stressing contenders and resource sensitive contenders. So what do we mean by this? Well, a resource stressing contender maximizes the stress on a particular resource by continuously making accesses to it that cause the most contention. So if we run a resource stressing contender in parallel with a task, this creates the maximum increase in execution time for the task due to contention over that resource, emanating from any possible single co-runner. And this allows us to define what we refer to as the resource sensitivity of a task, which equates to this increase in execution time when it is run in parallel with a resource stressing contender. Thinking about things the other way around, we can use a resource-sensitive contender. Now, a resource-sensitive contender suffers the maximum possible interference by repeatedly making accesses to the resource that suffer from the most contention. So running a resource-sensitive contender in parallel with a task creates the maximum increase in execution time for any single co-running contender due to contention over a resource emanating from the task. And this allows us to characterize what we call the resource stress of a task, which equates to this increase in execution time of a resource-sensitive contender when it's run in parallel with the task. And we note that resource stressing and resource sensitive contenders for a given shared hardware resource are not necessarily one and the same thing. So how do we go about quantifying task resource sensitivity and task resource stress? Well, as I just hinted at, we do this by using contenders. By using the resource stressing and resource sensitive contenders, this removes the problematic alignment issues, as these contenders continuously access the resource. So, looking at the top diagram on the slide, we can obtain the resource sensitivity of a task by running it in parallel with a resource stressing contender. The resource stressing contender continually accesses the resource, causing contention, and this increases the execution time of the task by an amount that we refer to as the task resource sensitivity. Looking at the diagram at the bottom of the slide, we can characterize the task resource stress by running the task in parallel with a resource sensitive contender. Here, any contention from the task will also be felt by the resource sensitive contender, which is continually making accesses to the resource. And this allows us to characterize the task resource stress, which is equivalent to the interference, the increase in execution time of the resource sensitive contender. Now, this interference can be subadditive, where contention is partly ameliorated by parallelism in the hardware. It can be additive, directly reflecting the bandwidth that's being used in the contention, or it can sometimes be superadditive, where the contention changes the state of the resource, causing operations to take longer. So if we want to quantify cross-core contention and interference between two tasks, then our proposed approach is to use the resource stress and resource sensitivity values for each of those tasks. Here, the maximum interference between the tasks is bounded by the resource sensitivity of the task we're analysing and by the resource stress of its co-running task. And this follows directly from how these terms are defined, and also from how resource stressing and resource sensitive contenders are defined. So if we look at the diagram on the slide, we can see that running a task under analysis in parallel with a co-running task, then the maximum interference on the task under analysis is given by the minimum of the resource stress emanating from the co-running task and the resource sensitivity of the task under analysis. However, considering interference as inflating individual execution times can be grossly pessimistic, so we need to extend these concepts to multiple tasks and their scheduling. Before we do so, let me formally introduce the system model. So we're interested in multi-core systems with M homogeneous cores, running partitioned fixed priority preemptive or fixed priority non-preemptive scheduling. The task model is an augmentation of the classical sporadic tasks, where each task has a standalone execution time, a minimum inter-arrival time, and a constrained deadline. However, here the tasks share a set of hardware resources, and each task is also characterized by its resource sensitivity and its resource stress to each of those shared hardware resources. The schedulability analysis concept is to consider interference over the time frame of task response times, using the total resource stress and the total resource sensitivity that occur within that time frame. So within the response time of a task, the worst case interference is bounded by the total resource sensitivity of jobs that execute on the same core as the task under analysis within its response time, and it's also bounded by the total resource stress of jobs executing on another core within that same response time. So this is illustrated by the diagram on the bottom of this slide. So you can see here we have a number of tasks running on the same core X as the task under analysis. And the blue region is the total resource sensitivity of the accesses made by these tasks. On another core, we have some co-running tasks, and the red region is the total resource stress emanating from those tasks within the response time of the task under analysis. And here the maximum interference on the task under analysis that can occur within its response time is simply the minimum of the total resource stress and the total resource sensitivity. So now we can put this into some equations. So if we look at partitioned fixed priority preemptive scheduling, first of all, the analysis derives from the standard response time analysis. However, we now have an additional interference term, and this interference term is an upper bound on the interference that may occur within the response time of the task under analysis due to interference occurring on a shared hardware resource from tasks executing on other cores. And this interference term is composed of these two components, E, which is the total resource stress emanating from one of the other cores within the response time of the task under analysis, and S, which is the total resource sensitivity from tasks executing on the same core as the task under analysis within its response time. So let's first of all look at the formulation for the total resource sensitivity. Well, this derives directly from standard response time analysis. We simply consider all of the jobs executing on that same core within the response time of task I and sum up their resource sensitivity values. Here we only need to consider jobs of the same or higher priority than the task under analysis, as they're the only ones that can execute within its response time. In formulating the total resource stress, we need to consider the jobs executing on another core Y within the response time of the task under analysis. And here we need to include jobs from all of the tasks, irrespective of their priority, since any of them could be running within the response time of the task under analysis. Now, there are three different formulations that we use that are given in the paper, and these lead to three different schedulability tests. The first test is context dependent, and it assumes that contention may emanate from a job at any time up to its own response time. The second test is also context dependent, and this assumes that contention may emanate from a job at any time up to its own deadline. And the final test is context independent. This test is fully composable. It assumes that any level of resource stress could be possible. And from these formulations, it's easy to see that there's a dominance relation between the tests. So the response time based test dominates the deadline based one, which in turn dominates the fully composable test. The schedulability analysis for partitioned fixed priority non-preemptive scheduling proceeds in a very similar way. First of all, we can derive the response time formulation from a sufficient test, and then we add on the interference term once again. Here, the formulation for total resource sensitivity is slightly different from the preemptive case, because here we've got blocking jobs of lower priority that may also execute within the response time of the task under analysis. It turns out that the formulations for total resource stress are exactly the same as before. Admittedly, they're past different response time values. And these form three tests with dominance relations between them. Priority assignment is an important factor in achieving high levels of schedulability in systems that use fixed priority preemptive or fixed priority non-preemptive scheduling. And in the paper, we were able to prove a number of results about optimal priority assignment policies for both the preemptive and the non-preemptive case. Now we'll consider schedulability test performance. The parameter settings used in our experiments considered tasks on between 1 and 4 cores of a 4-core system, with 10 tasks allocated to each core. The same task set utilization was used on each core, but different task sets were generated. Task periods followed a log-normal distribution in the range 1 to 100 milliseconds, and all of the tasks had deadlines equal to their periods. Resource sensitivity values were generated such that the total resource sensitivity utilisation, if you like, was set to some factor times the task set utilisation, and the default was 1/4 of the task set utilisation. We also ensured that the individual task resource sensitivity values did not exceed the task standalone execution times. Task resource stress values were set to some other factor times the task resource sensitivity values, by default 1/2. Task priorities were set according to deadline monotonic priority ordering, and 1,000 task sets were generated per utilisation level in the experiments. In the first experiment, we looked at the success ratio, that is, the percentage of systems that were schedulable, against task set utilisation for both preemptive and non-preemptive scheduling. Here we can see that more cores equate to more interference and hence lower schedulability for all of the tests. So we can see that performance is higher for 2 cores, which is in red, than 3 cores, which is in blue, and 4 cores, which is in green. We can also see the dominance relationships between the 3 types of tests, and this is evident in the comparison between the thick solid lines, which are the response time based tests, the dashed lines, which are the deadline based tests, and the dotted lines, which are the context independent or fully composable tests. In the second experiment, we examined the weighted schedulability metric. This metric allows us to vary some other factor, in this case the sensitivity factor, and see how that affects schedulability. Here we can see that a higher sensitivity factor, in other words, larger values of task sensitivity, equate to more interference and hence lower schedulability, and that the broad comparison between the different tests is similar to those in the success ratio graphs. In the third experiment, we examined weighted schedulability based on the stress factor. Here we can see that a higher stress factor, in other words, higher values of task resource stress, also equate to more interference and hence lower schedulability. And as the stress factor exceeds 1, then the total resource stress is nearly always larger than the total resource sensitivity, and this reduces all of the tests that consider contention to about the same level as the context-independent tests. In conclusion, the main contribution of this work is the multi-core resource stress and sensitivity task model and its accompanying schedulability analyses. This task model characterises how much each task stresses shared hardware resources and how much it's sensitive to such resource stress. The task model provides an effective interface between timing analysis and schedulability analysis, retaining the advantages of the traditional 2-step approach to timing verification. It caters in a generic and versatile way for a variety of different shared hardware resources. The schedulability analyses derived provide efficient context-dependent and context-independent schedulability tests for both fixed priority preemptive and fixed priority non-preemptive scheduling. These tests exhibit dominance relationships that illustrate the trade-off between context independence and schedulability. The schedulability tests were proven compatible or not with efficient optimal priority assignment algorithms, and they were subject to a systematic evaluation illustrating their effectiveness across a wide range of parameter values. Finally, I'd like to discuss a preliminary industrial case study. The purpose of this case study was to validate the task model. To do so, we obtained resource stress and resource sensitivity data for tasks from an industrial application to act as a proof of concept for the task model. Note, this is not intended to provide definitive values, which is a challenging research problem in its own right. The application comprised 24 tasks from a Rolls-Royce aero engine controller, with object code sizes between 300 kilobytes and 40 megabytes. This code was originally developed in Spark Ada and verified according to DO178C standards. It was originally designed to run on a specific packaged single-core processor, but has been ported to run on a Raspberry Pi. The hardware we used was a Raspberry Pi 3B Plus. This has a 4-core ARM processor with 16 kilobytes of L1 data cache, 16 kilobytes of L1 instruction cache, 512 kilobytes of L2 shared cache, and 1 gigabyte of main memory, DDR2 DRAM. The Pi was configured to run at 600 MHz to avoid any thermal throttling, and our main focus was on main memory as the shared hardware resource, since the level 2 cache was not used by the CPUs. Our experimental setup examined 10,000 traces for each of 24 tasks. Each trace is a job of a task with random values chosen for its input parameters. And each run was repeated 9 times to ensure consistency and to enable anomalies to be eliminated that were caused by the kernel scheduler tick and the clock synchronization interrupt. Each experiment paired a task with either a single contender or with a single different task. 3 different synthetic contenders were used that made read-read, read-write or write-write accesses to main memory. 100 accesses were done in the body of each contender loop to ensure that the loop overhead was small compared to the resource contention. And each read or write access compiled down to a single instruction. Finally, a handshaking protocol was used to ensure that the contender always started before the task and always finished after it. In our first case study experiment, we ran each task alongside each of the resource contenders. And for each task, we recorded the maximum values of the standalone execution time, the resource sensitivity, and the resource stress over the 10,000 traces with each of the 3 contenders. And here in the graph, we can see those sensitivity and stress values normalized to the standalone execution time. So here we can see that the resource sensitivity for each task varied from 3.8% to 15% of the task's standalone execution time, whereas the resource stress varied from 1.5% to just over 19% of the task's standalone execution time. And the ratio of resource stress to sensitivity varied from just under a quarter to just over 1.5. In the second case study experiment, we ran task versus task. For each task pairing, the maximum interference, that is the increase in standalone execution time, was obtained over 10,000 traces and compared to the bound computed from the task resource stress and task resource sensitivity values obtained in the previous experiment. So the graph here shows the maximum measured interference versus the bound for each of the pairs of tasks. So task 1 was paired with task 2, task 3 and 4 were paired, task 5 and 6 were paired, and so on. The maximum measured increase in execution time was no greater than the computed bound. On average, it was about 69% of the bound and varied between 26% and 99%. Thus validating both the task model and the underpinning concepts for this piece of research. So that brings me to the end of the talk. If there are any questions, I'd be pleased to try and answer them. Thank you.